All right, thank you very much for coming. Wow, my voice really projects through this microphone. Thank you very much for coming. Today, we're not going to talk about database technology as much as we're going to talk about real-time image recognition. So before that, a few fun intro slides. Oh, that froze. Cool. So we all know with the apps like Snapchat, with some of the technology that's coming out of Google, that the future of computing is visual. Well, it's also numerical too, right? So we'll still crunch numbers, and we still represent images as vectors and matrices. At the end of the day, those are numbers. But we know that the technology that's coming from companies like Google and making its way into pretty powerful computers that everybody has in their pockets now can do quite very amazing things. So for example, here, it's a Google app. You can point it at an item at a store, and it tells you what that item is. Or we also all know about Snapchat spectacles, right, that you can put on, and it augments your reality and records it. Another big presentation came out of Facebook where you can have your glasses, you can look at a table, right, that there's nothing on that table, but if you look through the glasses, you see augmented reality. So today, I'm going to talk a little bit how you can architect that type of infrastructure that enables that real-time response and real-time image recognition for your apps and for your applications. So I'll start with a customer of ours. The customer is in Germany. It's called Everybagde, Everybagde. And what I'm going to do, I'm just going to pull up their slide. Suspenseful music. More suspenseful music. OK, the internet is not cooperating with me here. So let's go back to the slides. The point of that is, in the meantime, I'll try to connect to my phone. The point of that is that if you have an app and you point it as a physical object, you take a picture of that physical object, and then based on that picture, you will find a product in their catalog that is very close to that image that you just took. So how does it work? Well, you start with developing a network, a machine learning neural network. And typically, the infrastructure that you use for it is TensorFlow, GPU processing, and you can scale it with Spark. Now, once you have this model produced, you want to take your database of all the images that you have in your catalog, and you want to go and extract feature vectors from each image, right? And what you can do then, you can store all these feature vectors in a memSQL table. So now I think that internet is available, and it's available through my phone. I can actually show you that demo, how it works in practicality. So this app that you're seeing on the website is powered by memSQL. So you take a picture of that phone. Then it thinks for a little bit. Most of the latency, as you can see later, is on the app side, not on the database side. And then it displays you all the similar objects in that massive catalog of products that you can possibly buy. So now you can imagine a lot of applications for this type of technology, right? You can augment reality. You can recognize faces in a security camera. You can admit people into your apartment based on security camera settings. You can do all sorts of image searches. You can go into a foreign destination, take a picture, and it will detect where you are located and give you like a little story about a particular building that you're pointing your phone at. So all of that stuff is possible with machine learning, with Spark, and with MemSQL. So let's go back to my example here. So I'm not going to go into the weeds of how you train that model. A lot of information is available online, and a lot of examples in TensorFlow, a lot of examples in Spark teach you how to go and identify those feature vectors that matter to be able to extract those feature vectors from each image. What I will tell you, though, is once you have those feature vectors in the database, we can process and identify those that are closest to the image that you just took with your camera in a very, very fast and scalable way. So, OK, so let's go to some database terminology. We'll create a table that's called features, right? That's where we're going to store feature vectors. And this features database is going to have only two fields, ID, which is an image ID, and a feature vector, which we'll just going to store in the binary format. So as we work with feature vectors in that table, we need to find which image is the closest. So the first thing we're going to do, we're going to normalize each feature vector down to the fact that the length of the scalar length of that feature vector is 1. So it's very straightforward. You just divide every element of that feature vector by the length of this vector. And now your vector has length 1. Now, the observation is that depending on how you construct your model, but if you construct it the right way, the similarity of two images is higher if the vector dot product of those two feature vectors are close to 1. Right? If features don't match at all, like you get something that's the dot product is going to be very close to 0. But if there's a lot of similarity, dot product is going to be a very large number, but that number is between 0 and 1. So now you can run this command, which is super straightforward for database people. Give me all the IDs from my table, where dot product of the field feature with the input. And that input is the picture that you just took and where you applied your machine learning model to extract the feature vector from it, greater than some constant, right? And you can tweak the constant. You can do some binary search to see what, if your model is good and if the constant is big enough that weeds out all the images in your database to the ones that are relevant and similar to the picture you took. So now, what is dot product? How many people know what dot product is? OK, well, I'm at the right conference. So everybody knows what dot product is. So I'm not going to repeat the definition here. But the interesting thing here that the dot product in that particular case is your similarity score. And the closer it is to 1, the closer the images are. So now, when you evaluate dot products, especially on matrices and on large matrices, especially when you do a lot of repeated ones, people use a lot of GPUs. However, the limiting factor here is, regardless if you use GPUs or CPUs, are going to be memory bandwidth, right? You have a large database of images, and that query in the database terminology is a full table scan. You need to go and touch every record in your table, apply dot product, look at the value of that product, and compare it to that constant that you specify in the table. So nothing you can do about it. You need to touch every row. How can you do it in real time? Well, that's where we can do some math, right? So first of all, let's implement dot product as fast as we can possibly do. And we'll do it so-called SIMD powerful implementation of dot product. Who knows what SIMD is? Okay, some people. SIMD stands for single instruction, multiple data. It's a technology in Intel CPUs and Intel and AMD CPUs that allow you to, in one tick, process a whole vector of data. Those vectors are not super large, but like 8 bytes or so, 8 integers or so. But still, by applying SIMD for vector DotProduct, you're improving your computations by 8 times, because this is a very, very scalable operation. Another thing that really helps is data compression, right? Those feature vectors can be put in a table, and the whole table will be compressed. And if your computations is fast, you can go as fast as memory bandwidth. Now, compressing allows you to scan less memory. And finally, it's query parallelism and scale out. MemSQL is a scalable system. You can run it on one machine, and I will show you some results on one machine. Or you can run it on 100 machines or 1,000 machines, and so you can just throw compute power at the problem. So let's do some math, right? So memory speed is about 40 gigabytes a second. A quick Google search will yield number 47 gigabytes a second, but we will just use 40 for simpler math. Each vector is 4K, so you'll get about 12.5 million images a second per node. I think my math is wrong here, and that's because I should round 47 to 50. So now it's more like it. But the cool thing is, if your database of images is 1 billion images, which is 1/10 of the world's population, and let's say we're doing face recognition, you can still, in 1 second, scan 1 billion images on a 100-node cluster. And today, a 100-node cluster for an enormous problem like this is not actually that much compute, right? You can go on AWS, you can spin it up, and you can start. It's very easy to provision. All right, so that's basically how it works. I'm going to show you a little demo right now, and this is going to be a database demo. Switching to a terminal, connecting to my VPN. Do SSH. So let's connect to MemSQL. MemSQL supports MySQL wire protocol, so you can very easily use a MySQL driver to connect to MemSQL. Now, this demo runs on one machine. And to prove this, I'm going to run a command that does not exist in MySQL, but it exists in MemSQL. It's called show leaves. And show leaves shows that there's only one node in the cluster. OK. I'm going to use the database images. Do you see me typing? Do I need to make it a little bigger? OK. So, and then I can say show tables. And this is my table features. I can describe my table features. And you see there are 2 fields, ID and the actual image. And that image is a binary field of 4 kilobytes. Now I will run select count star, not from images, but from features. And we have 12 million images here. All right, so that sounds good. And let's see how fast we can scan this table. So I already prepared a file that's called a.sql. As you can see, I cannot type really fast, so I'm using very simple names. And it says use images, select count star from features where, and those @ signs, there's actually DotProduct of image and some binary value. And that binary value, I just use 0x, AAA, and many, many A's. So now I can pipe this into the MySQL client to see how fast it runs. And based on our math, right, 12.5 million images, 4K images, and 50 gigabyte a second memory bandwidth, that should go in about 1 second. So I'm going to run this. OK, that went. Let's measure the time. Oh, wow. That went in 0.2 seconds. Any ideas how I could do it faster than memory bandwidth? No, there's no result caching. This is a full table scan. CPU cache, close. But if, it's 50 gigs of memory, right? So you need to scan 50 gigs. It's still, like, you cannot cache that. Compression. That's right. So all that data is actually compressed. And the compression ratio is right about 5x. So we're getting 5 times faster than a second. But the interesting thing there, and the big point here, is that we're not limited by compute. We're limited by memory bandwidth, how fast we can scan all that data that we have in our table. So this shows that we have an extremely efficient implementation of DotProduct. Under the hood, it uses SIMD. In fact, SIMD is old technology. Now Intel calls it AVX2 and AVX512. And AVX512 just allows you to have even larger vectors for primitive operations. But this is kind of what's possible to do on the database of 12 million images just on one machine. All right. So now let's talk about MemSQL. So what is MemSQL, right? So MemSQL is a real-time data warehouse. So it gives you storage, it gives you compute, it gives you petabyte scale, and it gives you world-class SQL query execution. Right? It supports high concurrency, it supports system of record, it runs on premises, it runs in the cloud. We actually introduced our cloud service on May 1st. And it allows you to have your operations real-time, make your operations real-time and operational. So you can use MemSQL to serve data to your customers, not just to produce reports, but to actually put it in production. Have people go into your system through apps, through websites, and querying MemSQL in real time. It's very compatible with the ecosystem, and particularly it's compatible with Spark. And that's what we see time and again, how this is a big advantage for our customers. Recently, we signed up a massive oil and gas company. One of the core requirements for them is deep integration with Spark. So how does that work? So the integration with Spark allows us to do massive data transfer between data frames and MemSQL tables using just a few lines of code. It's trivial to run a SQL statement and map it to a data frame. And it's trivial to take a data frame, call save to MemSQL, and it will drop all this data back into MemSQL. That really allowed us to rise on the Magic Quadrant from Gartner for data warehouses. Data management solutions for analytics is the same thing as data warehouses. All right. So we all know Apache Spark, right? I'm not going to ask who knows Apache Spark. This is the conference I'm in. It's fast and general purpose engine for large-scale data processing. And Spark and MemSQL work really, really good together. So let's understand, what do you use MemSQL for, and what do you use Spark for, and how do you use them together to drive the most value? So first of all, Spark, it's fast and large scale, and so is MemSQL. Like, it's really fast and it's really large scale. Spark gives you general purpose compute engine. You can munch your data frames, you can perform various, you can apply various operations to them, and then you can write lambdas in Scala or Python or Java and plug them in. MemSQL focuses on SQL. We have our own extensibility, but that extensibility is kind of, it's more controlled. It's very similar to, for those who know Oracle or PostgreSQL, to PL SQL. And MemSQL is great for SQL, for computations, for SQL computations. It's also great for persistence, right? You can store data in SQL, and you can expose that data like in any other database to many people querying that that very same data at the same time. And it supports very high levels of concurrency. It supports transactions. And it supports a large number of BI tools. So it plugs into like Tableau, Looker, and whatever that might be. And like I said earlier, the integration between MemSQL and Spark is a very fast cluster-to-cluster bidirectional data transfer. This is an example of that architecture that we talked about earlier. We start with a database of raw images. You use Spark to train the model. I would advise to also integrate Spark with some of the deep learning frameworks such as TensorFlow or Caffe and whatever. But the bottom line is that Spark gives you that scale out, so you can train in parallel. And then once you have that model, you can also use Spark to apply that model to every image in your database. This will produce feature vectors. Once you have feature vectors in a data frame, you just call save to MemSQL, boom. You have all the feature vectors in a MemSQL table, and now you can power your application or your website with MemSQL. And using that very simple command, select ID from features where DotProduct is greater than some constant, you can get all the similar images. So that's all I have, and we have about 5 minutes for Q&A.
We got about 8 because the clock's wrong.
Oh, OK.
Check, check. All right. Put your hands up, and I'll just come to you. Do you have any questions? All right. I'll come to you.
Thank you for the presentation. And a very quick question. So in a typical use case, do you usually deploy the two things separately or in the same machine or in the same cluster? I mean, from the architecture view.
So normally people put it on separate clusters. It is possible to put them on the same cluster, but Spark is memory hungry. And MemSQL is not super memory hungry, but it likes to control the memory on the machine. So in production, we see people deploying MemSQL and Spark separately. Now, for development purposes, there's no harm for deploying it on the same machine.
But then in that case, the networking bandwidth will be the bottleneck, which cannot leverage the biggest power of the MemSQL.
Yeah. So I just want to clarify that at the time where all the feature vectors are already in MemSQL, there is no Spark. Right? The application connects directly to MemSQL and runs that select statement. Now, when you are training the model and when you're transferring feature vectors from a data from some other place into MemSQL, that's when you use Spark. And it's a bulk operation. So we basically can do it at the at the network bandwidth speed, which is quite high.
OK, so in the use case of for example, for the use case of the image recognition, if the online input is at a very high throughput, we still need the Spark to do the incremental update or incremental lookup in the MemSQL. So in that case, well, can you say something?
Yeah. So let's step back a little bit and then elaborate on the use case. So you have your catalog of products. And then for every image in your catalog of products, you already have a feature vector that's stored in MemSQL. Right? And then your apps are hitting MemSQL at high concurrency and getting the results back. Now, you're constantly adding or modifying your product catalog. And so you need to re-extract feature vectors and maybe even retrain models. So if you retrain a model, guess what? You need to update every single feature vector in that thing. Then you will invoke that bulk operation. This will certainly put some amount of pressure on MemSQL, right? Because you need to update all those values. But at the same time, it's, MemSQL is a concurrent system. It has a workload manager, so it will prioritize those operations in one way, and then all your customers that are online and hitting MemSQL will will still have enough bandwidth. This also depends on the size of the cluster. You can always throw more compute at the problem. Yep.
All right, we got a few back here.
In the live inference step, when you receive an image coming from a phone, can you describe how you transform that into a feature, what the best methods are?
Yeah, so let's look at the... Well, that's usually a little bit of a know-how for the end users of MemSQL. So what we do very well, we provide infrastructure for people to, run DotProduct, run other vector operations at the memory speed. We do have a little bit of insight of what they actually do, right? So this particular customer, they use TensorFlow, and they use some of the latest and greatest image processing techniques that they do to train the vectors and identify those features. I believe they went through a manual process to identify those features manually and then trained it to extract values towards those features.
I'm curious if, for this application, if they explored doing something like an approximate nearest neighbors method to at least narrow down the list to avoid doing that full table scan. And if they explored it, why didn't they decide to do it? You
could. And that company that we're working with, and that's not the only one, we also work with a nonprofit called Thorn that does image recognition. They played with nearest neighbor. It was not accurate enough, and that gave them a more accurate kind of search. And at the same time, you might think, oh my God, full table scan. But if you do it at memory speed, it's 50 gigs a second, right? And then across the cluster. So you can actually afford it and not think about it.
So why DotProduct adds similarity metrics? Why not do the Euclidean distance, or so it's still the element by element operation, right? So
why DotProduct? Why not something else?
Yep.
Is that the question? The direct answer is that's what the customer wanted, right?
Okay.
They across the use cases that we see, they solved that particular problem with DotProduct. I can see this could be solved by, I don't know, subtracting two vectors and doing modular on every feature.
Yeah, I mean, the absolute differences are like any Euclidean distance would
Any
also
Euclidean
work,
distance
right?
will do.
Yeah. So, and how do you okay, so you have the threshold of having the dot product greater than 0.9, right? How do you set up the threshold? There might be cases where dot products, so even though the dot products is less than 0.9, they might still be similar, right? So how do you handle such situations? So we might have some left out images in similarity results.
Well, if let's just look at this image, right? So you take a picture of a glass, then it goes and finds all the stuff, and for them, being slightly inaccurate is okay, right? They just need to rank them in a certain way. So they don't want absolute accuracy. So
is there any case where you can have because it's just a number, and then you can have even for images which have different intensities in different places, it's possible that they might have higher dot product values, but still dissimilar.
But they have higher dot product values, but the images are not similar?
Yeah.
I guess that's possible. And if you do, so again, looking from the infrastructure perspective, right? I kind of believe that these guys do a good job doing feature engineering and extract just the right features, so the similarity is going to be there, and that's their core expertise.
Yeah, actually, that just started from how they are representing the features. This might be 0 thresholded, or these might be the values from 1 and -1. So yeah, I was just curious.
Yeah.
Thanks.
And I have only limited insight of how they do it.
All right, I think we've got time for one more.
It's a great talk, first of all. One typical question regarding the productionized in-memory database is how much time it takes for you to bootstrap. For example, your machine was down, and then you want to bring it back.
Oh, so this particular workload is not in memory. So this particular workload is on disk, but cached in memory. So if you look at the table definition here, use images, show, create, I can't type, table, features. It says clustered column store here, which just indicates that this is a column store table, and MSQL stores column store tables on disk. So that's why I'm saying petabyte scale. I don't expect you to put all the data, all the petabyte of data in memory. Now, all that data is cached as you query it. And now, coming back to your question, what is the time for you to restart the system? It's pretty much instant, right? Because the data is only cached in memory. The first time you query is you're going to have some I/O cost, of course.
All right, everybody give a round of applause to Nikita. Thank you very much.